Hey guys, welcome to the engineering world. Here is the lecture series for GATE IES 2021. Hey guys, support my work and subscribe our channel. Give me the support, I will give the best. Here is the queuing theory part 2. For part 1, please go through the link in the description box. Here we will discuss about customer behavior. First one is bulking. An arriving customer may not join the queue if there are many customers in the system. Let me explain how. This is a system. Yes. Then there is a queue, long queue. Customers are standing in the queue. Then one of the arriving customer want to join this. Then one of the customer want to join this queue, but he did not because of long queue. Hence he go back. This is known, and hence customer bulk. This is known as bulking. Then the next is reneging. Here the person joins the system, but after some time decides not to continue and simply moves out of the system, called a reneging. That is, he bores or he think queue is not moving as fast as he considered. Then jockeying. Customer may jockey from one waiting line to the another. There are two servers or two systems, 1 and 2. These are the customers in the first one. Let me try it. Then this is in second. After some time, the customer in the first queue or line or waiting line observed that second line is moving fast, and he or she quit the first line and joined the second. This is known as jockeying. Okay. Then the expected number of customers in the system and queue, or average number of customers in the system or queue. Let me tell you the difference between length of the queue and length of the system. Actually, queue is the part excluding server. Here I am showing the queue length, and it is a system length. So in system length there is a inclusion of server, but queue length is limited only to the of customers, that is queue length, or only of that excluding that server, and system plus server, queue length plus server. This difference is important because many of the students don't know what is queue length, what is system length. So system length, server plus queue length. Okay, this is a customer is being served. Okay, this is server and this is customer being served. Then this is important formulas. Expected or average number of customers in the system, LS. LS is equal to rho upon 1 minus rho, where rho is utilization factor, as we discussed in first lecture, is equal to lambda by mu. Lambda arrival rate, mu service rate. If you want how it is arrived, this formula, I am providing NPTEL video link of 1 hour lecture. You can refer that link, but I think no need of it. Just remember these formulas. Okay. Then the next is expected or average number of customers in the queue, that denoted by LQ. LQ is equal to rho into LS. This is also present in the NPTEL video. You can refer it or just mug up these formulas. It is sufficient. Remember, average number of customers in the system denoted by LS. Okay, and expected or average number of customers in the queue, LQ. Please, this is the most important formulas. Then expected waiting time in the system and the queue. By the Little's law, according to Little's law, expected waiting time in the system denoted by WS is equal to LS upon lambda. Then what is the Little's law? Actually, it is asked in GATE 2010 that what is the Little's law. So correct answer is it gives the relation between expected waiting line in system to the expected customer number in the system. This, that is WS is equal to LS upon lambda. This expression also present in that NPTEL video, but please just refer these formulas. Then expected waiting time in the queue. What is the expected waiting time or average waiting time in the queue? It is given by WQ is equal to rho into WS. What? Rho into WS. Same as the length of the queue and length of the system. Same formula, same pattern. Then what is the significance of LS and WS? Actually, LS is used to calculate the non-production time or idle time or waiting time cost of customer. This is important. Cost of the customer, non-production time or idle time or waiting time cost of customer. LS is used. Here is the formula. Non-production time cost per unit time, okay, is equal to LS into non-production time cost per customer per unit time. Remember this formula. If they ask cost of customer, only cost of, that is waiting time cost of customer, then use this formula, LS into non-production time cost per unit time per unit. This. Then for WS, if non-production time cost per unit time is given, non-production time cost per unit is given, then total non-production time cost in rupees is estimated by WS value. You can say rupees or dollar or euro, it's questioner choice, so it's WS. Then total non-production time cost in rupees or dollar or euro, you can say whatever, is equal to WS into non-production time cost per unit time. Remember these two formulas only. No need to remember other things. Okay, total non-production time cost and non-production time cost per unit time. Let's see here examples. It is asked in ESE 2007. If average arrival rate in the queue is 6 hours and average service rate is 10 per hour, which one of the following is average number of customers in the line, including customer being served? Okay, given average arrival rate lambda is equal to 6, then average service rate mu is equal to 10, then we have to calculate rho utilization factor. Rho is equal to lambda by mu is equal to 6 by 10 is equal to 0.6. So customer number of customers in the line including customer being served, that is length of the system. They asked the length of the system, hence LS is equal to rho upon 1 minus rho. So answer is 1.5. Then the next question, ESE 11. For a single server queue, the mean arrival rate is equal to 8 per hour and the mean service rate is 12 per hour. The expected number in the waiting line is equal to, here waiting line, expected number in waiting line, that is we have to find WQ, given lambda 8, mu 12, then rho lambda by mu 8 by 12, then LS rho upon 1 minus rho is equal to 2. We have to find expected number in waiting line, that is LQ. Remember waiting line, expected number in waiting line, LQ rho into LS 1.33. okay, waiting line, not a system. We have to find in waiting line. That's it. Hope you got it. These type of questions are asked in only GATE and ESE. Answer is 1.33. Then the next is ESE 16. A self-service store employee, one cashier at its counter, 8 customers arrive on an average every 5 minutes. Okay, 8 customers, that is lambda is equal to 8 customers per 5 minutes. Cashier can serve 10 customers in the same time, that is mu is equal to 10 per 5 minutes. Assuming Poisson distribution for service rate, the average time a customer spends in the queue, average times customer spends in the queue. Okay, so that is we have to find WQ. I'm not going to calculate WS directly. I'm going to calculate WQ. That is, first we will calculate WS, then WQ. Lambda 8 upon 5 minute. Okay, rho 8 by 10. Calculation ALS, rho upon 1 minus rho is equal to 4 by Little's law. WS is equal to LS by lambda is equal to 5 by 2. Then WQ, average time in customer spent in the queue, WQ is equal to rho into WS is equal to 2 minutes. That's it. So average time spent in a queue, WQ, we have calculated. Okay. Then the probability density function. Here also just formulas, just mug up them. Okay. Pn, let P of n is equal to probability of n customers in the system. Remember, system is equal to rho raised to n 1 minus into 1 minus rho. Rho raised to n into 1 minus rho. This formula's derivation is also present in the NPTEL video. If you want, go through that video, link in description. Okay. If n is equal to 0, that is number no customer in system, that is server is idle or system is empty. Okay, question can be framed on these three statements. Okay, no customer in system, or server is idle, or system is empty. Then P of n is equal to 0. Simply apply mathematics. You get 1 minus rho. 1 minus rho, just 1 minus rho. That is no customer in system, system is idle or system is empty. Probability 1 minus rho. Then the next is n is not equal to 0. That is at least one customer in the system. Okay, 1, 2, at least one. Okay, or system is busy. One customer in system means system is busy. That is probability of n is not equal to 0. That is probability of n greater than or equal to 1. Got it? So by probability we get 1 minus P of 0. That is rho. Let's consider rho raised to 1. Similarly, we can find that probability of at least k number of customers in system is equal to rho raised to k. That is probability of n greater than or equal to k is equal to rho raised to k. Remember this formula. At last, I will give all the formulas. Just take screenshot of that one. It's sufficient for you. Then the next is probability of more than k number of customers in system. That is more than k means k plus 1, at least k plus 1. Got it? If more than 1, that is 2, 3, 4, that is at least 2 if we considered 1. Okay, so probability of n greater than or equal to k plus 1. Got it? Is equal to rho raised to k plus 1. Probability of more than k number of systems, rho raised to k plus 1. Let here consider problem. Customer doesn't have wait before service and more than 2 customers in the service. You have to calculate. The given is mean arrival rate 6 per hour, service rate 10 per hour. Okay, that is lambda 6, mu 10 as usual. Then rho is equal to lambda by mu, that is 0.6. Customer doesn't have to wait before service means system or server is ideal, no customer in the service. That is probability of n is equal to 0. That is directly 1 minus rho is equal to 0.4. Okay, directly we get 0.4. Then more than 2 customers in the service. More than 2 customers, that is at least 3. Got it? More than 2, that is maybe it may be 3, 4, 5. So at least 3, that is rho raised to 3. That is we will get 0.144. In GATE 2018 set 2, they ask us one question about this one. Just see that problem. Arrivals follow Poisson distribution with an average 30 customers per hour. Then we have to find the successful customer arrival between 1 and 3 minutes. Actually formula is, we have to first find in 0 to 1. Sorry guys for that technical error. Here are the important formula. I will give the link of that text in the description box. Really sorry. Just take the screenshot of these formulas. Rho is equal to lambda by mu. For our calculation purpose, rho is less than 1. Rho utilization factor or traffic intensity. LS rho upon 1 minus rho. LS expected length of system or number of customers in the system. LQ rho into LS is equal to expected length of the queue or expected number of customers in the queue. WS is equal to LS by lambda by Little's law. WQ rho into WS, and probability of n, that is probability of n customers in the system, is equal to rho raised to n into 1 minus rho. Just remember these formulas. By the way, thanks. This is our first wing theory, means first chapter of Imor is completed. Please give me the support. I will give the best support. Subscribe our YouTube channel. Hope you will learn something new. All the best. Thanks.